One problem that gave people difficulty on exam one was this problem right here. I was actually meaning for this problem to be fairly easy for people, but it was difficult. In part A, based on these equations, these formulas for these functions, you were supposed to find a simplified formula for G. People had trouble with function notation, really, in understanding what to do. That was part of the difficulty. And then even if you understand the function notation, there were still mistakes in the simplification, and some people didn't actually simplify. And then part B was to describe the transformations, shifts, which represents translations, reflections, stretches, and compressions that can be applied to the graph of f to obtain the graph of G. So f is your parent function, your basic x squared function, and G is some transformed version of f. So part A is, again, a matter of understanding function notation, which is something I said when we were first talking about this, is something I've told you that people do have difficulty with, understanding what to do here. First thing is to realize this is not f times x plus 1, even though it's kind of consistent with that type of notation. F is not a number, it's a function name. This is f of x plus 1, and you need to understand that that means take whatever this expression is, it's an x plus 1 in this case, go up to the formula for f and replace x with it, no matter where the x or x's are. In this case, it's a fairly simple function, just x squared. So I need to replace x with x plus 1 and square it. That's what this part becomes. This f of x plus 1 is right there. But I am also multiplying it by 3 and then adding 2. So that's if you got this far, that's like worth 2 out of the 4 points, but you also need to simplify it. That's part of the directions, find a simplified formula, which means expand it into standard form. And so this is x plus 1's quantity squared. It's x plus 1 times itself. You need to FOIL it. You've got to use first times first, outside times outside, inside times inside, and last times last. Before you multiply by 3, and before at the end you add 2, you need to also understand the order of operations. So if I FOIL this, use parentheses, x times x is x squared. Outside times outside is x times 1, x. Inside times inside is also x. X plus x is 2x. And then last times last is 1 times 1 is 1. Okay, that you got to square this. The answer is not x squared plus 1. You also need an extra 2x in there. And then distribute the 3 through the parentheses. Get 3x squared plus 6x plus 3. Don't forget the plus 2. The final simplification is 3 plus 2 is 5. So there's your final answer for part A. Part B, you're supposed to relate again the graph of G to the graph of F by transformations. There were lots of people who were looking at this final formula for that. That's not what you should do. All you have to do is look at this right here, actually. You don't even have to know the formula for F. You need to think about that formula in terms of transformations. It involves a leftward shift by 1 unit because of the x plus 1. A vertical stretch by a factor of 3 because of the 3 out here, and then a vertical shift upward by 2 units because of the plus 2 there. Actually, the order you do things in is important. It is important to do, well, either the leftward shift or the vertical stretch first, and then the vertical shift upward by 2 units last, technically speaking, because if you do the vertical shift upward by 2 first, before you, for example, multiply by 3, you'd really be multiplying the entire thing by 3 if you did it that way. That's not what to do. Now, I wasn't picky about that. If you just said the right transformations, but not necessarily the right order, I gave you full credit. So you could say, again, a leftward shift or translation by 1 unit. It's leftward because it's a plus 1 there. This is one thing that's confusing for people, because when there's a plus 1 there, they think it should be rightward because right is like the plus direction. But when it's in the input for the function, it actually is leftward. And a way to see that is to ask yourself, what would I plug in for x that would give me an input of 0 here, for example? -1 is what you would need to plug in for x to give me f of 0. So g of -1, if g of x were just f of x plus 1, would be the same as f of 0. It's like taking the graph of f and shifting it to the left by 1 unit. Vertical stretch. Many people said compressions, but compression kind of implies squishing, not stretching. Vertical stretch by a factor of 3. And it is a factor, really. It's a multiple 3 times f of x plus 1. And then a vertical shift up by 2 units. Okay, so don't look at the simplified formula. Some people said shift upward by 5 units because of the 5 there. You got to look at the unsimplified formula, because you're trying to relate it to the graph of f, not the graph of 3x squared plus 6x, for example. I think sometimes it's the time pressure of an exam that sort of makes people's brains freeze when they see problems like this or something. It's really not that difficult of a problem, but you need to understand what's going on, and you need to practice problems enough that you sort of glance at problems like this and you sort of know what to do ahead of time, but it's just a matter of carrying out the details. 11 gave people trouble as well, as it often does. Graphs of trig functions, maybe even in the pressure of an exam. Write your formulas in one of those 2 ways to get this graph. You have to identify the amplitude, the vertical shift, the period, those kinds of things. Notice that the maximum value is 5 and the minimum value is 1. The vertical shift is going to correspond to the average of those 2 numbers. The average of 5 and 1 is 3. Yeah, this horizontal line at 3 is going to be the vertical shift. That means D is going to be 3. That's the vertical shift. Whether you use the cosine or the sine, it doesn't matter. That'll still be the vertical shift. The B is determined by the period. That's the horizontal distance from peak to peak. Now, I didn't give you the coordinates of that point, but you should be able to figure it out. This first coordinate's 6. This one's 12. This one's got to be 6 more. It's got to be 18. The coordinates of that point's got to be 18, 5. So this horizontal distance right there is 18 minus 6 is 12. 12 is the period that I often call it capital T. So that means the B is 2 pi divided by capital T. 2 pi divided by 12 simplifies to pi over 6. So that's the B. Again, whether you use the cosine or the sine, I'm not saying yet whether you should use the cosine or the sine. The amplitude is the vertical distance between the midline and the highest value. That's 2. It's also the distance between the midline and the lowest value at 1. Okay, the amplitude is positive 2, but that doesn't mean A is positive 2. It could be negative 2. And since the graph starts at its lowest point when T is 0, it's best to use a cosine with a negative 2 in front. So what I was looking for in your answer was y equals, using this one, negative 2 cosine of pi over 6 times x plus 3. Now, that's not the only way to write the answer as far as this graph goes. It is the only way to write an answer in one of these 2 forms. If you wrote it in a different equivalent form, I did still give you full credit. One example of an equivalent form, if you prefer using the positive 2 for A, but still cosine, is to replace x with x minus 6, so to involve a horizontal translation. Then plus 3, and there were a few people who did it that way, and I gave you full credit. You could also actually use a sine if you use a horizontal translation, realizing the coordinates of this point are going to be 3, 3, horizontal translation to the right by 3 units for a sine. You could also write this as 2 sine of pi over 6 times in parentheses x minus 3 plus 3. Any of those answers got full credit. Though technically this was the only one that fits one of these two patterns. Okay, but if you did with horizontal translations correctly, that's fine. Do you need to multiply the pi over 6 through the parentheses here or here? If you did it correctly, I still give you full credit, but you don't really have to. These specify the horizontal translations more clearly when you leave it like that. And it is minus because it would be rightward translations. Actually, there are infinitely many ways to write the answers. These are just the most common ways. But I was seeing people, again, maybe in the rush of the exam, realizing they needed to think about the amplitude in the period, but they were just writing things down. There were people who were looking at this amplitude and thinking it was 3, for example. There were people who were looking at this period and were thinking it was 6 or something. There were, in the rush and pressure of an exam, mistakes made, even if you maybe knew the basic right idea, caused problems to happen when you actually wrote down your answer. H of x is this function. You're trying to find its derivative. And I'm telling you what the rules to use. The power rule right there, and this linearity of the derivative operator right there. That's a 3.1 subject, but we did talk about it a week ago. And I'm telling you what it is, so you should still have been able to use it. When you look at this formula for h of x, you could think of this function as being like the f of x, and this function as being like the g of x, if you're trying to use that formula there. So you could write h prime of x is f prime of x plus g prime of x. Yes, here I'm using the ddx notation, and here I'm not, but it's not a big deal. It means the same thing, the prime and the ddx. Did you have to identify what f and g are? No, you didn't. I'm just trying to be explicit about what they are if I want to use this rule. And then for both of those functions, just use the power rule. In the case of f, the n is 4, and in the case of g, the n is 1/2. So just use this formula. When n is 4, you get 4x to the 4 minus 1, which is 4x cubed. And when n is 1/2, you get 1/2 x to the negative 1/2. 1/2 minus 1 is negative 1/2. A few people wrote negative 3/2 there, I think. So there is the answer, and that's all you had to do. Most people got at least 1 or 2 points on number 13 here, but there's probably only a quarter of the class got full credit. Identify points where it's not continuous and not differentiable. The not continuous is easier, I think. Just x equals 2. Obviously, there's a jump discontinuity there. It is continuous everywhere else. You're not picking up your writing utensil anywhere else. The graph is connected those other spots between 0 and 2 and between 2 and 5. Where is it not differentiable? Anywhere you have a discontinuity is a place where it's not differentiable. And if you don't have a formula, if it looks like a corner, assume it is a corner. It's also not differentiable at 4. Also, if you do not have a formula, if you've got a place where it looks like there's a vertical tangent, you should assume there is a vertical tangent. It's also not differentiable at 3. Okay, that's something I emphasized a week ago. If you've got a formula, the looks could be deceiving. Maybe if you zoom in, it's really not a corner. Maybe if you zoom in there, the tangent's not vertical. But if I don't give you a formula, then you can't zoom in. So you should assume I'm not trying to trick you and go with what it looks like it is. 14 probably gave more trouble than it should. Estimating a graph of the derivative of this. Key things I was looking for is, first of all, identifying where the tangent lines are horizontal. At about these two values of x, x is around 1.4 and x is around 3.3 or so. Those would be two spots where the derivative is 0. The derivative is positive over here, and negative in there. It's got to go down and back up again. It's got to look like a parabola. Should you try to estimate the slope here, for example, reasonably accurately? Yeah, I think you should have a reasonably accurate estimate for the slope. There is somewhat close to 2. If you draw a tangent line there, looks like the slope is close to 2. Do you have to say it's exactly 2? Not necessarily. Somewhere around 2. And drawing a smooth graph looking something about like this. And yeah, minimized near the inflection point of the original graph, or technically at the inflection point of the original graph, which is when x is right around 2.4 or so. Okay, so there's a reasonable graph of the derivative. Some people got the basic shape right, but did weird things like putting weird curves in here. Maybe trying to plot points and imagining that they should connect them with weird curves. No, it should look, this does look like a cubic. This should look like a quadratic. Should look like a parabola. Is this a cubic and is this a parabola? Not necessarily, but it looks that way. So draw it reasonably close. The limit definition of the derivative gave people trouble as well, mostly again because of function notation issues. So the function here is the distance fallen. Fallen is a function of time, 4.9 t squared. Oh, one thing that came up for maybe 3 of you in this class is you were thinking of that as a height and thinking even though you got an answer that was positive, that the answer had to be negative. And so you switched your sign to negative. It would be a negative velocity if we were talking about velocity here, but this is not height. This is distance fallen. You're dropping something and measuring how far it falls. So it falls a certain positive distance. And so the derivative of this is, I mean, you could call it a velocity, but it's a downward velocity. But the downward direction is taken to be negative because this is a positive quantity. As it falls downward, this is growing through positive values. It's keeping track of how far it's fallen. So it's better to think of it as a distance traveled, and it's better to think of the derivative perhaps as a speed, and you get a positive number. As far as doing this limit, again, keep the limit sign there as you go. Only get rid of it at the very end. Some people were sloppy about that. And understand function notation. F of 1 plus h, go to that formula, replace t with 1 plus h. So you get 4.9 times the entire quantity 1 plus h squared. Minus f of 1. F of 1 is 4.9 times 1 squared. It's the 1 that's getting squared. That's the value t. Some people, for some reason, squared the 4.9. Order of operations is to plug the number in for t, square that, and then multiply by 4.9. So there's the limit you have to calculate. Now it's a matter of simplifying correctly. Once again, I have to FOIL. Maybe to be careful, leave the 4.9 out there first. 4.9 times 1 squared is another 4.9. Now use the distributive property to get 4.9 times 1 plus 4.9 times 2h is 9.8h plus 4.9h squared. Some people got the right answer, even though they were making some mistakes in here. I am grading not only right answers, but also your work and whether your work is right. So you would have missed a point or two, depending on how many mistakes you made. The 4.9s cancel. With what's left, you can factor out an h and divide that out. And so you're ultimately taking this limit. What you're left with there is a nice continuous function of h. Now you can get rid of the limit sign because now you can plug in h equals 0 and get 9.8 meters per second. Don't forget the units. This turned out to be the same answer as part A. Part A, you also should get 9.8 meters per second. Why'd you get the same thing? Isn't part A an average speed and part B an instantaneous speed? Yes. And so in general, they're not going to be the same. But in this case, they are. It turns out with a quadratic function, as this function is, that if you find the average speed between 2 points, time 0 and time 2 in this case, which is the slope of a secant line, it will equal the slope of the tangent line halfway in between. With quadratic functions, that works. With cubics or whatever, cosine, sines, that doesn't work. But with quadratics, it happens to work. The average speed between time 0 and time 2 turns out to be the same as the instantaneous speed, the derivative, at time 1, which is halfway between 0 and 2. Those two slopes turn out to be the same. I did not ask you for reasons, but if I did ask you for reasons, you should be able to give them. And I guess I'll say right now, I'm not ruling out, if I give you a problem like this in the final exam, also asking for reasons. So I'm saying it right now. You should spend time thinking about it, not only right now, but maybe later today, maybe in a week, maybe in a couple months before the final exam, for sure before the final exam. Give reasons for these steps. That would be the definition of the derivative. That this limit equals f prime of 1. I told you that. But if you had to give a reason, it would be because that's the definition of the derivative. To get from here to here, all you're just doing is algebra. I'd be okay with just saying algebra for the reason. If you wanted more detailed reasons, it's really the distributive property applied both when you do foiling and, well, I guess in going from here to here, but I'll just also call that algebra as well. This step is also algebra. 3 steps of pure algebra. Is there anything else that's not just algebra? Yeah, this is not just algebra there, even though it seems like it. This is more than just algebra. It's algebra and something else. It's algebra and the definition of a limit. The epsilon delta thing, though you don't have to mention epsilon delta. Why is it the definition of a limit? In that definition with the epsilon and delta, when you're letting x approach some number c, you're thinking about it not actually equaling c. The absolute value of x minus c is also bigger than 0 in that definition. X doesn't actually equal c. The value of the limit is independent of what happens to this function at c equals 0 in this case. Doesn't matter that this function is undefined there. Doesn't matter. These two functions as functions of h are equal as long as h is not 0. So if this one has a limit as h goes to 0, so will this one, and they'll be the same limit because they're the exact same function when h is not 0. And again, when h is 0, it's irrelevant for the limit, technically speaking, as far as its definition goes. But then we end up plugging in h equals 0 at the end anyway. Well, that's only because this is a nice function. It's continuous. This is continuity. Continuity of what? Continuity of this function. That's a nice linear function. Graph is a straight line, no holes in it. The graph of that one's a straight line as well, except there's a point missing. There's a hole at h equals 0. It's a removable discontinuity. This formula fills in that discontinuity. You can now evaluate the limit by plugging in h equals 0. And this last f is, well, you could call that arithmetic if you like. Arithmetic meaning adding, multiplying, that kind of thing. So I'm saying right now, you should be able to, if I could put a problem like this on the final exam, I'm saying be able to do more than the calculations, be able to give reasons. Maybe if I did something like this on the final exam, I would just do part B and not part A to save a little time. But part B is the harder part, so you need to make sure you practice that. And then the last one is the proof. Also gave people trouble, as expected with proofs. Proofs of this logarithm property. I wrote the key equations you need to use in the proof without writing the proof in sentences because it would have taken too long to grade everybody's exam that way. When you do a proof for a problem like this, I mean, you certainly can practice it ahead of time. You certainly could put a little piece of your note card with a proof like this and just mimic it. But I hope you understand. You need to, it's better to work on understanding proofs instead of just mimicking them. And there's always, with logarithm proofs, 2 keys. One key is just definition of what logarithms are. And the other key is a property of exponents. This property of logarithms is related to some property of exponents. What property? Well, it takes a little experimentation perhaps, but it's related to the fact that, let me use different letters, a to the m minus n is a to the m divided by a to the n. How do I know it's going to be related to that? It's because of the minus sign there, and the minus sign there matches. It's got to be related to this property because of the minus sign. And here's what I wrote on your papers, if you didn't do it correctly, is I said, okay, we need to show these 2 things are equal. Let's make them both powers of b and show that the resulting powers of b are equal. If we can do that, that means those powers are equal. Here's what I mean more explicitly. If I take b to the log base b of x minus log base b of y, all that thing being 1 power of b, does it equal b to the log base b of x over y? That's what I'm hoping to show. If I can show that, that means those exponents are equal and I'm done. Oh, I got the difference of two numbers in that power. Now I have to use this property here. With b playing the role of a, let this log playing the role of m and this log playing the role of n. Use it. B to the log base b of x divided by b to the log base b of y. Sometimes there's just so many symbols. It's like, what does it all mean? It's easy to get confused. But that's what I did there. I applied that property. Now use the definition of logarithms. B to the log base b of x is just x, right? Because log base b of x is the power I got to raise b to get x. So if I raise b to that power, I got to get x. It's self-fulfilling. It's like a self-fulfilling prophecy. Seriously. B to the log base b of y is y, because log base b of y is the number I've got to raise b to get y. So if I raise b to that power, I got to get y. Done. And this is just a number. What was I trying to do? I was trying to show that this is the same as b to this thing. But that's just the definition of a log as well. This is just a number. If I raise b to the log base b of that number, it gives you that number. Same reason as this giving you that and this giving you that. And that does it. I've got b to this power equaling b to this power, therefore the powers must be equal. Technically, that also requires the definition, the fact that b to the z power as a function of z is a one-to-one function. If the outputs are the same, the inputs must have been the same. If you didn't say that, I still give you full credit. And there were a few people who got full credit, but they're probably 10 to 20% of the class got full credit. Then you'd want to take this and write sentences. What kind of sentences? Start by saying, by definition of logs, this equals that, and this equals that, and this equals that. Then say by a property of exponents, this equals that, and then essentially finish that line of equations. So this is the essence of the proof, the key of the proof. And you just have to put it in a sentence structure. Don't be afraid when doing problem solving or proofs in the future, even on an exam, to do a little scratch work before you write the actual proof. Because people just sort of make the mistake of just going in right away on the proof. I mean, that could be okay if you've studied it so well, you know exactly what to do. But most people don't know what to do right away. You need to do a little scratch work to help you do a little problem solving as well.